take like 3, 2 3/4, 4. Don't even know. A lot of work in post. Sedimentary rocks. It's honestly a bit ambitious, verging on sinful, to try and make a single video about sedimentary rocks. I mean, we're talking about the category of rock that covers 75% of Earth's surface. As such, consider this fair warning that we will not, simply cannot, nor should we, sufficiently cover a topic as large as sedimentary rocks in this video. As a reminder, this video, like my minerals video, which you should go watch, it'll be relevant, link is in the description, are designed to complement the introductory geology curriculum taught here at University of Wisconsin, and as such, aren't meant to be comprehensive. That said, I think my previous video on minerals, again, worth watching before this one, go do it. You'll thank me later. As I always say, what was I saying? As I always say, I think my previous video was a little bit long, and as such, I'm trying to keep this video to less than 15 minutes. So, sedimentary rocks in 15 minutes. This seems silly, but I'm gonna do my best anyway. Let's start the timer. Okay, sedimentary rocks, unlike metamorphic or igneous rocks, are exclusively formed at Earth's surface. That's because sedimentary rocks, by definition, are the amalgamation of bits of other things that are all compiled and packed and turned into a rock. The fancy term for this is lithified or lithification, but don't worry too much about that. So there are 3 main categories of sedimentary rocks, and those are siliciclastic, biochemical, and chemical. We'll start with chemical and biochemical sedimentary rocks, since they're kind of related, and those ones are formed by the precipitation of ions out of water. And this simply means that there are a bunch of little chemical elements called ions that get dissolved into lake water or seawater that, through different processes, are turned into biochemical and chemical sedimentary rocks. It's a bit abstract, I know, but I'm going to kind of do my best to illustrate here. So in the case of biochemical sedimentary rocks, this precipitation is done via little aquatic critters like mollusks or coral polyps, for example. And these critters use the ions from the seawater to build their homes, whether it's the shells on their backs or the reefs in which they live. And this is a perfect example of an ancient coral reef that is considered a biochemical sedimentary rock because the coral polyps built it. They use the ions from the seawater to build these structures in which they live. Then, when they die, their homes accumulate on the ocean floor and eventually get turned into or lithified into a biochemical sedimentary rock. So you can basically think of biochemical sedimentary rocks as graveyards preserved in the rock record. Chemical sedimentary rocks, on the other hand, are a little bit different in that they don't require these little critters to pull the ions out of the water and form a rock. You know, it might actually just be easier if I kind of show you what I'm talking about with these. Whoa. Interesting. Oh, that's new. Huh. My hair's gone. What the heck? Didn't see that coming. Well, this is pretty much what I had in mind. This is about perfect here. We were talking about chemical sedimentary rocks. Another thing we call them is evaporites because often that's how they form. What happens is water gets trapped in a closed basin like this. You see there's no way out for water or stream to leave this basin. And as water gets trapped here, it gets super salty. And then as in this hot, arid environment, water inevitably evaporates, that remaining water gets saltier and saltier because as the water evaporates, the salt gets left behind. And there's a point, which we call a tipping point, at which enough water evaporates that the salt has nowhere to go, and it precipitates out or falls out in solid form in these crystals like this. And that's how we get evaporative or chemical sedimentary rocks. And my guess is actually that this stuff is probably gypsum, which is the same exact stuff that you have in your salt shaker at home. Pretty neat. Oof, man. I'm gonna have to work on that. Shirt, hat, rocks. Where were we? What's left? Oh, Siliciclastic sedimentary rocks. Say that 10 times fast. Yikes. Siliciclastic sedimentary rocks. So all siliciclastic means is that constituents that make up this type of sedimentary rock are primarily silicate minerals. And if that doesn't make sense to you, seriously, go watch my minerals video. Link is in the description. Do it. It'll help. All right, recall that sedimentary rocks, right, are all formed at Earth's surface, right, and are composed of suites of pre-existing constituents. So for biochemical sedimentary rocks, those are the leftover bits and parts of dead critters that have piled up and turned into a rock, right? For chemical sedimentary rocks, they're little mineral crystals precipitated out of the water. For siliciclastic sedimentary rocks, the constituents are bits and pieces of other older rocks, which themselves could be made up of other older rocks, which could be made up of older. It's kind of like a dream. What a rough dream. Grad school is destroying my subconscious. What was it about? I guess we should talk about how siliciclastic sedimentary rocks form. So, yeah. When geologists think about siliciclastic sedimentary rocks, they think in terms of sources and sinks. In other words, where did the sediments found in any given siliciclastic sedimentary rock start? And then where did they collect before they were lithified or turned into a rock? But before a siliciclastic sedimentary rock is even a possibility, the sediments have to be generated so that there's stuff to make into a rock, of course. And this is where terms like weathering and erosion come into play. We'll talk about weathering first. So there are two types of weathering, chemical and physical. And physical is, as it sounds, simply the physical breakdown of some pre-existing rock into smaller bits. And one example is when tree roots grow into rocks. You may have seen it. When they continue to grow, they break that rock up, right? Another great example is the freezing and thawing of ice. So as water seeps into a crack and then freezes, it expands and breaks it up. In fact, these two processes, tree roots and ice, are, and you've probably seen this, the bane of sidewalks all over the world, right? And processes like these are the primary sources for siliciclastic grains, like these guys. Chemical weathering, on the other hand, is responsible for the generation of most of the chemical ions and elements that precipitate out as either chemical or biochemical sedimentary rocks. And chemical weathering can generally be thought of as the chemical dissolution or altering of minerals into their elemental constituents. And for the sake of time, I'm going to skip the equations, but you've probably heard of acid rain, right? Well, the acidity in rain is a good example of something that can chemically weather rocks exposed at Earth's surface. And once a rock is weathered into either smaller pieces or into a chemical solution, the next step is transport or erosion, right, from source to sink. And this takes place in a myriad of different ways, but you can pretty much think of anything that can transport grains, especially in the terms of siliciclastic sedimentary rocks, as being really important in this stage of their formation. And so things like wind and water, especially like a river, for example, are huge players here. So once the grains in these siliciclastic sedimentary rocks have been weathered out of their parent rock, they've been eroded and transported from their source to their sink, they've been deposited and then lithified into a siliciclastic sedimentary rock, there are things that geologists look at that tell us about the history of the grains that make up these rocks, right? And these are texture and composition. And texture can be thought of simply as the characteristics of each grain. Because as it turns out, each grain tells a pretty interesting story about how it got to be where it is. And as geologists, we look at things like the shape and size of the grains, as well as if the grains in any given rock are well sorted or not. What do I mean by that? Well, I think there's another good opportunity to bounce back out into the field. close. Oh, this is perfect. Nice. Yeah, this is exactly what I had in mind. So we're talking about texture, right? And there's kind of three things that geologists like to think about when we're thinking about texture, at least in terms of siliciclastic sedimentary rocks. And those are sorting, grain size, and grain shape. So when I'm talking about sorting, I'm talking about the size of grains relative to the grains around them. So if we look at this rock right here, we see that there's these enormous grains like this guy and this guy and this guy. But there's also all this smaller stuff around it. And so this is a wonderful example of a very poorly sorted rock. And we actually call this conglomerate, which is by definition super poorly sorted. But sorting tells us a lot about the depositional environments in which this rock may have formed. For example, if this were formed by a river, you can think of a river as it moves, right, carries a bunch of sediment. So if it's a raging river moving super fast, it's going to carry huge cobbles and boulders and stuff and big grains like this down here. But if it slows down, then those won't be able to get, moved downstream and they'll fall out. As the river slows further and further, slows slower and slower, it'll deposit finer and finer grains. We can actually see that progression here, right? So if we look kind of at the base here, we get these huge grains in here, right? And then right above them, those big grains are gone, right? And then right above that, those medium grains are gone. And so we know that through this section here, actually, the river that was responsible for depositing this slowed down. And so that's actually pretty cool. We can tell the depositional environment from just looking at grain size. The other things we look at are size of grains and shape of grains. And you can imagine as rocks break off in the mountains, they're probably really big and really sharp and really jagged. But as they, tumble further and further away or get moved further and further away by rivers, those rocks will break down and get smaller and smoother. So something like this, which is really big and not exactly round, is a young sediment in terms of how far it's traveled. So it's probably pretty close to where it started. Whereas if we go all the way down here, we see that this stuff here, these are actually really small grains. This is a very fine or a fine grained sandstone. You'll just have to take my word for it. But it suggests that these grains have existed at least in a river or been transported for a lot longer or a lot further than the stuff just above them. We can tell that just looking at the size and shape of the grains. You also notice that this is really well sorted because all the grains are the same size. So this tells us the difference between what deposited this up here and what deposited this down here. So we know there's a huge shift in the environmental setting right here in between these two rocks. So looking at shape and size and sorting in siliciclastic sedimentary rocks helps us understand where these grains came from, how far, how long they've traveled, as well as the differences in environments in which all of these different rock types were deposited. It's actually really cool stuff. Oh my gosh. All right, where were we? Yeah. Siliciclastic sedimentary rocks, right? We were just talking about texture. Recall that there's texture and composition, the two things that we look at when we're looking at siliciclastic sedimentary rocks. And so now that we know that texture can give us a little idea about the history of a grain, let's chat briefly about composition. All right, if you still haven't seen my minerals video, this is where things might get a bit confusing because understanding composition is dependent on some basic knowledge of mineralogy. So this is your last chance. Just do it. It'll help. So as it turns out, certain minerals weather out of rocks faster than other minerals. And this means that the further a grain or a rock gets transported from its source to its sink, the more concentrated certain minerals like quartz become. Recall from the minerals video that quartz is a silicate mineral whose chemical composition is SiO2. Its crystal structure and chemical composition are such that it's super stable at Earth's surface, meaning that it's hyper-resistant to both physical and chemical weathering and therefore sticks around a lot longer than most of the other minerals as it's transported from its source to its sink. You ever been to the beach? You ever notice how all of the little sand grains are pretty much the same color? Well, in most cases, that's because they're all quartz. And they're all quartz because nothing's left. Nothing else is left. Where those grains started, probably up in the mountains, there was quartz, there was feldspar, there was micas, there's all sorts of different minerals. But as they all got transported, Everything else weathered out, and quartz is all that left. It's pretty neat, huh? So what this means is that simply by looking at the suite of minerals in any given siliciclastic sedimentary rock, we can say something about how mature or immature that rock is. That is it made up mostly of quartz, or are there a bunch of other things in it as well? As you can imagine, the sediments in a more mature rock with a bunch of quartz will have traveled further from their source than immature sediments. I like thinking about it in terms of people. Like my grandparents, for example, have lived longer and seen more than a less mature person like me. All right, for the sake of time, I think I'm gonna call it there. Obviously, I've left out kind of a lot of stuff, specifically a big one, sedimentary structures like these awesome ripple marks in the sandstone. But maybe I'll have a chance to make another video in the future, talk a little bit more about sedimentary rocks because there's just so much to talk about. But until then, I hope you go check out some rocks, and that's exactly what I'm going to do. See you later.
Yeah.
I'm still here.